On September 7th, 2025, something impossible happened. The world watched the moon vanish behind Earth's shadow, but what came next is what truly stunned everyone. Moments into the total lunar eclipse, the sky erupted. From horizon to horizon, a brilliant neon green light washed over the night. Amateur astronomers, armed with backyard telescopes and DSLRs, scrambled to capture what was happening. They spotted a streaking, icy blue comet that in an instant shifted impossibly to a glowing emerald. And that color, it clung to the night, refusing to fade even after the eclipse ended. Online forums exploded into chaos as professionals and hobbyists alike hunted for answers. That was the night 3-2 Atlas arrived. Our third confirmed interstellar visitor, already accelerating past Mars at an astonishing 98 kilometers per second, carrying mysteries no telescope on Earth was ready for. The question burned in everyone's mind. Why would a comet from another star system paint our skies with a color science couldn't explain? Just hours after the eclipse, the first images started trickling in. They came from backyard telescopes in Buenos Aires, from rooftops in Nairobi, and from the outskirts of Lisbon. On the raw, unprocessed frames, a pale blue streak cut across the shadowed sky. But then, its hue deepened, saturating into a green so intense it refused to fade even as the moon slid free of Earth shadow. In São Paulo, a student with a borrowed camera caught the exact moment of the color shift in a burst of 10-second exposures. The timestamps, anchored to 3:18 UTC, lined up perfectly with a sudden massive spike in amateur chatter online. "Never seen that shade of green holding after an eclipse," one post read. Another user added, "The color, the speed. It's screaming not local." In Cape Town, a retired engineer logged the object's movement through his 6-inch telescope. He noted a velocity so rapid that even a few minutes between shots showed a clear displacement against the starfield. The comet's apparent motion, nearly a quarter of a degree per hour, defied all expectations for any known visitor from our own solar system. Across Europe, observers compared notes on that persistent emerald glow. They argued over filters and calibration settings, but the raw data all told the same story. The green lingered. It refused to wash out under city lights or fade with the moon's return. In the hours that followed, forum threads ballooned with uploads. We saw stacked images, spectral traces, even hand-drawn sketches. Metadata poured in from every corner of the globe: coordinates, exposure times, filter bands. A teacher in rural Turkey posted a time-lapse that captured the color transition frame by frame. Meanwhile, a high school astronomy club in Morocco measured the comet's position shift against background stars, confirming its breakneck pace. By dawn, the evidence was global and unmistakable. The object's color and its incredible speed were unlike any comet in living memory. The amateur networks, usually slow to agree on anything, converged on a single stunning conclusion. This was no ordinary visitor. The world's professional astronomers, who had been silent until now, were about to receive a flood of data they simply could not ignore. By 7 a.m. UTC, the phrase "the night the sky went green" had already become a trending hashtag. From tiny backyard rigs to colossal 10-meter giants, the world's telescopes were now pointed at a single, fast-moving green visitor. The handoff from public curiosity to scientific urgency was complete. The clock was ticking, and every minute counted. Let's rewind a bit to July 1st, 2025. Inside the control room for the Atlas survey in Hawaii, the first data drop from their robotic telescope triggered a familiar script. An automated system ran the new detection through the orbit solver, checked for known asteroids, and flagged anything that looked out of place. But this time, the software stalled. Every attempt to fit the object's path into a closed, elliptical orbit, the kind that keeps things bound to our sun, spat out errors that refused to settle. The numbers pointed to a path that didn't loop back, a path that didn't belong to the sun. The eccentricity was greater than 1. The orbit was hyperbolic. This wasn't just a statistical fluke. It was a mathematical wall. A small team of analysts gathered around the screen, watching as the error margins climbed with every new calculation. Standard protocol called for waiting, for collecting more data to rule out a false alarm. No one wanted to be the one to clog the global confirmation pipeline with a mistake. But the object's apparent speed and its bizarre trajectory just kept breaking the model. A log entry from 3:14 UTC captured the growing unease. "If this is real," it read, "it's interstellar. If not, we waste the world's time. One analyst, recalling the frantic scramble to observe Oumuamua, our first interstellar visitor, pushed for escalation. They pinged the minor planet center with an urgent note: path unclosed. Eccentricity greater than 1. Possible ISO candidate. The debate in the control room shifted from caution to rapid calculation. How many hours did they have until follow-up observations became impossible? Every minute lost meant a shrinking window to study this thing. By 5 a.m. UTC, the team moved as one, prepping a global alert. The interstellar flag was officially raised. For only the third time in history, the software could not bind an object's orbit to our sun. The Minor Planet Center alert went out at 5:12 UTC on July 1, 2025. It was stamped with the object's preliminary designation and a stark warning: orbit fitting failed. Eccentricity above 1. Outbound velocity unbound. Within hours, the object received its formal name: 3-2 Atlas, the third confirmed interstellar object, following in the footsteps of Oumuamua and Borisov. The datasheets told a story in stark numbers. At its discovery, 3-2 Atlas was already moving at an incredible 61 kilometers per second relative to the Sun. Trajectory models projected its speed at its closest approach would be nearly 98 kilometers per second. That's fast enough to cross the distance from the Earth to the Moon in just over an hour. It was far beyond the reach of any probe, any rocket, or any planned interceptor we had. This was a one-time pass, a cosmic drive-by that would never repeat. The impossibility of interception settled in quickly. No existing mission, not even the fastest solar sail concepts still on the drawing board, could hope to match its velocity or trajectory. With its closest approach to Mars set for October 3, 2025, at a distance of nearly 29 million kilometers, the window for any kind of close-up study was vanishingly narrow. The notification process, once a quiet formality among astronomers, now triggered a global scramble for remote observations. Every telescope, every spectrograph, every available eye on the planet was needed before 3-2 Atlas slipped away for good. Spectrographs from La Palma in the Canary Islands and Gemini South in Chile began streaming in their data before sunrise. Analysts pored over the raw outputs, searching for the familiar chemical fingerprint of C2 or diatomic carbon. That's the molecule responsible for the classic green glow in nearly every comet we've ever seen. But the data told a different story. The strong, clear signature of C2 was missing. In its place was something else, a series of bright, narrow emission lines clustered in the green part of the spectrum, between 520 and 540 nanometers. These lines didn't match any known molecule you'd expect to find in a comet. It wasn't C2, it wasn't cyanide, it was completely alien. The mystery deepened. If it wasn't the usual suspect, C2, what was making this comet glow with such an otherworldly green? And why was the color so persistent, lingering in the atmosphere long after the comet itself had passed? Gas phase analysts, the experts in this field, were stumped. They ran simulations, cross-referenced databases of exotic molecules, but nothing matched. One team in Germany proposed a wild theory. Could it be a form of ionized oxygen, O2+, being excited in a way we've never seen before? It was a long shot, but it was the only hypothesis that even came close to explaining the spectral lines. But that raised an even bigger question. To get that much ionized oxygen, the comet would need to be shedding water ice at a truly colossal rate, far more than its size would suggest. And even then, what was providing the energy to keep it glowing so brightly for so long? The comet wasn't just a passive block of ice and rock. It was an active, energetic system doing something completely new. The science was failing to keep up with the phenomenon. The world had just a few short months to solve the puzzle of the green comet before it vanished back into the interstellar darkness, taking its secrets with it. Something strange was happening in the night sky. Telescopes around the world were pointing at a faint smudge of light, a visitor from beyond our solar system named 3IATLAS, but what they saw broke all the rules. The comet was glowing with a vibrant, intense green light. Normally for comets, this green hue is a dead giveaway for a molecule called D-carbon, or C2. It creates a specific signature, like a chemical fingerprint, that astronomers know well. But when they analyzed the light from 3IATLAS, that fingerprint was gone. Instead of the sharp telltale peaks of dicarbon, there was just a broad, featureless green plateau. It was like hearing a perfect C note played without a piano. The color was there, but the source was a complete mystery. And the weirdness didn't stop there. When astronomers looked closer, they expected to find water, the lifeblood of most comets we know. But 3I Atlas had flipped the script. The dominant gas wasn't water vapor. It was carbon dioxide. In fact, CO2 outnumbered water by a staggering 8-to-1. A ratio never before seen in any comet from our own cosmic neighborhood. This completely upended the expected chemistry. All the usual reactions driven by water just weren't happening. Scientists scrambled, looking for other explanations. Maybe it was cyanogen? No, not enough of it. Carbonyl sulfide? Barely a trace. Every standard explanation failed. For now, the only thing they knew for sure was that 3I Atlas had rewritten the rulebook on what a comet could be. As the world's largest telescopes locked onto this cosmic enigma, another shocking discovery lit up their screens. This time it was in the ultraviolet spectrum. The data revealed more than 20 distinct, sharp lines of nickel. There was no mistaking it. But the strangest part was what wasn't there: iron. In the cosmos, nickel and iron are almost always found together, like cosmic partners. But in 3I Atlas, iron was practically a no-show. Just a few weak signals, barely detectable. The ratio was completely lopsided. In some observations, nickel outshone iron by a factor of 50 or more. For scientists who study comets, this was like finding a fingerprint from another world entirely. Back on Earth, lab teams worked around the clock, trying to replicate these bizarre findings. The leading suspect became a class of compounds called nickel carbonyls. These are incredibly volatile substances. In a lab, they can turn to gas at temperatures as cold as -25 degrees Celsius. But in the unimaginable cold of interstellar space, they could potentially survive for billions of years, just waiting for the warmth of a passing star to be released. This could explain the abundance of nickel. Iron, on the other hand, tends to get locked up inside rocky, silicate grains, making it much harder to detect in a comet's coma. This interstellar visitor wasn't just a curiosity. It was a messenger, carrying clues about the chemical processes happening in the coldest, darkest corners of our galaxy, far from any star like our own. The comet's dust told another part of the story. Analysis showed that the light scattering off its dust grains had a strong negative polarization. This is a characteristic usually seen in objects from the frigid outer reaches of our own solar system, like those beyond Neptune, not in comets that swing close to the sun. This, combined with images from the Hubble telescope, painted a picture of a small, compact nucleus, probably only a few kilometers wide, wrapped in a dense cloud of CO2 and highly unusual dust. The physics of this dust, tightly packed, fine-grained, and strangely cohesive, suggested it was born in an environment vastly different from our own, far beyond the normal frost line where comets form. The stakes for scientists were getting higher. This wasn't just exotic chemistry. It was a direct clue to how planetary systems might form in the most extreme environments in the galaxy. But time was running out. As 3I Atlas continued its journey, it was getting closer to the sun from our perspective on Earth. Soon, the sun's glare would blind both the Hubble and the James Webb Space Telescopes, our most powerful eyes on the sky. The scientific community had to act fast. If they were going to get a final, detailed look at this object, there was only one option left: a daring and unprecedented maneuver that would turn our attention to the red planet. All eyes turned to Mars. With Earth-based telescopes about to be blinded by the sun, the only way to intercept 3I Atlas during its most critical phase was from orbit around another planet. The mission fell to two unsuspecting spacecraft, the Mars Reconnaissance Orbiter and MAVEN, both already deep into their own scientific missions studying Mars. On September 10, 2025, a high-priority memo landed in the inboxes of their mission managers. The order was clear: drop everything and prepare for an immediate target of opportunity campaign. The comet would sweep within 29 million kilometers of Mars on October 3rd. It was a golden opportunity, a chance for their higher-resolution instruments to dissect the comet's coma and tail in ways impossible from Earth, but only if they could seize the fleeting moment. The decision was controversial. Mars climate scientists protested, worried about interrupting years of crucial atmospheric data. Engineers worked furiously, rewriting targeting software and repointing sensors. But the science was too compelling to ignore. In a move that shattered normal procedure, NASA pushed through full approval in just 48 hours. By the end of September, the Martian outpost was on high alert. Instrument teams rehearsed their observation sequences over and over. They knew the comet's incredible speed, nearly 98 kilometers per second, left absolutely no room for error. Then, on October 3rd, as 3I Atlas made its closest approach, both orbiters executed their commands perfectly. They captured a flood of data spectra, ultraviolet flashes, and atmospheric readings. In just 3 hours, MAVEN returned more information on the comet's metal vapors and structure than most missions gather in an entire season. The high-stakes gamble had paid off. For a brief critical window, Mars had become humanity's frontline observatory, our only eyes on a truly unique visitor from the stars. In the aftermath, as scientists pored over the incredible data from Mars, engineers back on Earth were facing a difficult truth. 3I Atlas hadn't just appeared out of nowhere. It had slipped past our defenses. A review of archival data revealed that our automated sky surveys, like TESS, and the Rubin Observatory had actually spotted the comet more than a year earlier, in late 2023 and again in mid-2024, but the signals were faint, fast-moving traces, barely above the background noise. The detection algorithms, designed to filter out anomalies and avoid false alarms, had seen the comet's odd color and its unusual trajectory and quietly discarded it. In trying to be efficient, we had ignored the very thing we were looking for. The postmortem was swift. Software developers began rewriting their code, creating new systems designed to flag exactly these kinds of outliers in real time. The new mandate was simple: no more missed interstellar visitors, even if it meant more false positives and late-night alerts. But mission architects argued that better software wasn't enough. If we couldn't guarantee an early warning, then we needed to be ready to act at a moment's notice. Suddenly, proposals that once seemed like science fiction were on the table. Fleets of rapid response interceptors, nimble solar sailcraft, and swarms of tiny CubeSats, all designed to launch within weeks of a detection. The goal? To chase down any future interstellar object, match its incredible speed, and study it up close before it could vanish back into the darkness. The lesson of 3I Atlas was written in every line of new code and every blueprint for these future missions. Cosmic surprises demand readiness, not regret. We now know that every interstellar visitor is a unique time capsule, carrying priceless information about how planets and stars are born across the galaxy. We missed our chance to get up close and personal with Oumuamua and Borisov, our first 2 visitors. We watched 3I Atlas from afar. But for the next one, we'll be ready. Ready not just to watch but to meet it halfway, and unlock the secrets it carries from its home among the stars. Thanks for watching. If you found this journey as fascinating as we did, be sure to like, subscribe, and hit the bell for more stories from the frontiers of science.